Okay, we are ReadOX, and we're a new company that's got a grand mission that over 5 years we're going to develop the technology for measuring what's going on at a subcellular level to add to the technology, to bring nanotechnology into medicine in a very, very important way. And we want to deal with age-related diseases as an immediate market and ultimately deal with lifespan extension and rejuvenation technologies. This is our target with the cellular organelles. Since I talked about this earlier, I'm going to skip over this fairly fast, even though this is part of the technical presentation. This is the cycle of what we're measuring here to identify the effectiveness of the mitochondria and how well it's functioning. If you have any questions about that, I'd be glad to get to it. And I'm going to go on to the business side of things. This is a pre-existing research where the mitochondria have been tagged, and so this is one of the technologies that we might use to identify pH changes that take place within mitochondria. We're interested in looking at the energy production capabilities and looking at the intermembrane space that accumulates proton gradient as measurements of how well the mitochondria is functioning, and our goal is to be able to measure individual mitochondria, how well they're doing. So we will be able to assess the population of mitochondria within a cell to see how much variation there is and how much genetic damage might be accumulating, how many of them are senescent, and then after some kind of therapy, how those numbers have changed. There's all kinds of technology that's out there for measuring metabolic rate, looking at how well mitochondria do. And the ones that are relatively easy to use and in clinical practice deal with things like oxygen consumption and CO2 emissions, and looking at the ratio between those to study the energy situation. And of course, one of my favorite techniques as a biohacker is to measure thermal effects, looking at body temperature changes. But the idea is that we take all of this new material that we're going to do and put it into a device. Well, first we're going to put it on a lab bench in the first 5 years, verify it and establish its clinical utility, and then we're going to miniaturize it. So hopefully within 20 years we'll have a fully FDA-approved implantable device for doing near real-time assessment of energy systems in the body. Why this has not happened in the past? A lot of this has to do with regulatory barriers and what is considered a disease. And the FDA's mandate is to approve things for treatment of disease, and up until recently, aging has not been considered a disease. A whole wide range of different capabilities are going to be needed for us to accomplish this goal. We're going to need to do cellular techniques for isolating, but not only cells, but cellular organelles. We're going to need to be able to vitrify samples very rapidly to preserve the redox status that's taking place in those cells, so that our intervention is not ruining that data and we're not collecting good data. We're going to have to fabricate things, we're going to have to miniaturize technologies, we have to put it all together, so we're going to need a broad range of expertises to accomplish this. We're also going to need huge amounts of data analysis. This is going to generate raw data, and we need to do correlations between the data that we collect and physical manifestations, disease manifestations, performance manifestations. Our goals are what we're going to look at in terms of judging what we're doing and whether we're effective is to look at first to be able to define the space we want to occupy, to look at all the different parameters that would have a direct bearing on mitochondrial energy production. ATP, NADH for reducing equivalents, the ability of glutathione to handle oxidative stresses. Any of those that we're going to put on the table, we will then use as benchmarks to establish the validity of our new measurements that we make. And of course, the ability to predict clinical outcomes is what's going to drive medical acceptance of this technology. So the first product we hope to offer is the medical analysis services that we want to get CLIA certification for the technology so that we can market it to doctors and we can collect data from the marketplace. And then eventually we want to be able to insert probes into mitochondria as we're preparing to miniaturize everything for an implantable device. 5-year, 10-year, and 20-year projections in terms of money requirements. The bulk of it is in the long term about the miniaturization of the device. We look at that as our biggest challenge, but the idea is that we get into the marketplace relatively early in the process. I'm sorry, I'm having problems with buttons. We're getting into the process, early in the thing. In the first 5 years, we do our animal studies, we collect our data, we show our efficacy, we demonstrate that this is feasible, that we can actually collect this data precisely and accurately, and then within 10 years, we go towards being able to market this test and have the marketplace adopt it in practice. 5-year milestones, development of the bench device, 10-year milestone to make it into something that's implantable, a standalone device, 20 years to make it miniaturized. So 5 years, we actually have the functional device, or at least it does most of the stuff. We know what we're trying to measure. We've got our targets already identified. We're collecting data on them, and we can do single cell analysis, and the ultimate goal to be able to look at a single organelle, to be able to establish the function of a single mitochondria, or if we can, develop an analysis of lysosomes and peroxisomes. Of course, all the data is based on early work with animals, and we hope to have that completed by the 5-year milestone. The minimal viable product. Thank you. We should have that ready by 10 years, where we don't need to have the miniaturization already accomplished. That as a technological development may be the most challenging things we have to face, but once we've established the efficacy of the product and the value in the marketplace, going for miniaturization and implantability becomes then a defensible investment. Of course, laboratory certification and a completion of a phase 1 trial. 20-year milestones, the nanoscale device, and successful integration of this technology into medical practice. Markets. Medical diagnostics, the obvious one that we're going after initially. Assessment and repair, mainly assessment, but in terms of repair, we're looking at a way to prove and monitor repair efforts. So whatever clinical procedure is employed, we can do before and after comparisons to see, is this working or is it not? Or possibly, has the bottleneck in energy production shifted from one place to another place? Environmental toxicity monitoring is one of my favorite topics, looking at the role of, for example, heavy metals, endotoxins from the microbiome, mycotoxins, and their effect on mitochondrial function. This is something that we can measure from an effect point of view. These compounds have a direct toxic effect on the mitochondria. We'll be able to measure that and even make judgments about what kind of microbiome supplements and changes that might be made clinically, which ones are going to address that mitochondrial problem, which ones do address that mitochondrial problem. Sleep apnea monitoring, an obvious application that you're looking at respiratory rate and oxygen as an input into that, so certainly this would be able to monitor that kind of thing. And for looking at diet exercise habits, those kinds of things, for lifestyle management, that this is a foundational health monitoring device that will take the current trend towards wearables into the next generation. Funding sources, government funding sources for early development. The idea of enabling the military to fine-tune soldier training programs to measure not only from the performance of what they see in the field, but being able to look at them biochemically and assess their mitochondrial function as a way of optimizing their training programs. With the current administration, a lot of the funding for basic research is being discouraged, and this is one way to make this attractive to military funding opportunities. Insurance companies is one of my favorites, because if you can prove to the actuarials of insurance companies that something is real and that you're saving people money and you're improving their health, then it's real. And lastly, eccentric billionaires. Obvious corporate issues and management in terms of science, a broad range of experts, and in terms of taking it to the market, the legal IP and regulatory issues. So that's it, and I'll open it up for evaluations and questions.
Judges, do you have any comments, questions, especially questions?
Questions. How do you localize a pH measurement at the subcellular level?
The proposal that's on the table is to take a 2 nanometer proton-only pore. It's a tube that only allows protons to flow down the middle and push it through the membrane to allow protons from inside the compartment to transverse the membrane, and then having some kind of detection device on the end of the tube. This has obviously never been done, but...
Is mitochondrial pH an important facet of mitochondrial?
Yes.
Mitochondrial state?
Yes, so here we have the diagram of what we're going to measure, and right here we have the pH compartment. So all of these oxidative phosphorylation enzymes of this battery system here occupy the membrane that is on the inside of the mitochondria, and they're pumping protons.
What else besides pH?
We measure also redox couples, the lactate to pyruvate ratio. Lactate is the reduced form of that molecule, or that backbone, and pyruvate is the oxidized form. NADH is the reduced form, oxidized form, reduced, oxidized, reduced, oxidized.
Are you going to get all of those? You're not going to get all of those just from the protons.
No. The proton measurement is just another way, an independent way to assess mitochondrial function. So if you have a blockage in the conversion of protons into ATP, you're going to see that pH drop. So it's one way to monitor the flow of energy through the mitochondrial system from a intermediate stage. You're not only just looking at the output of it in terms of ATP or the output of it in terms of NADH, but you're looking at one of the steps in the middle so that you can verify when something's going wrong where the problem is.
So is the idea, there's lots of mitochondria per cell. Is the idea to go after them in parallel or sequentially?
All of the above.
What fraction of the mitochondria do you imagine yourself sampling?
Well, if we can sample them non-destructively, there could be a widespread sampling, and maybe you might look at 1% of the mitochondria just to get a profile.
So a small fraction.
Well, yes, when you're dealing with 5,000 mitochondria, looking at 50 is going to give you some data on it, but that challenge of whatever implantation technology would be involved in trying to stick a needle into 50 different mitochondria from a device that sits outside the cell, we don't know how to do that yet.
Destructive or non-destructive?
Right, yes.
Non-destructive?
Well, to start with, we're on the lab level, it's destructive. But hopefully we can make this non-destructive so we can get real-time data. Or it's possible that it could be destructive in that we have a device that sucks an entire cell into a system and breaks it down and looks at it. And the idea being that a single cell, loss of a single cell in, let's say, the liver, wouldn't amount to anything. And that one could do one cell and then a day later do another cell and a day later do another cell, or you could do a cell an hour, you could do a cell a minute, and it could be destructive and we'd still get that kind of data in a way that might be considered medically acceptable and ethically acceptable.
But then you can
So can you hold on, we're the judges.
Are you ready for a question, David?
Yeah. So I'm curious as to why you are going right to animal studies. I mean, it just seems to me all you need would be cell cultures.
We can do that. We would do cell cultures.
Right.
Yes.
And really, you need to mature the technology before you're moving right there. I would be very surprised if within 5 years you could interrogate individual mitochondria. So I don't know where you're going to.
No, that would be a longer scale, longer time scale. But the idea is when we first start off, we'll be doing massive parallel identification of these variables. We'll be separating cells from tissues, breaking the cells down, and stratifying all the organelles, and then pulling out specific organelles and looking at the chemistry that's going on inside those by sacrificing those cells and organelles.
Dave, part of the reason of doing the animal phase in that stage was we don't have a longevity profile. And so if you take a mouse study and examine the mitochondria over the course of the entire lifespan of a mouse population, you might get a better understanding of what to expect from human longevity data. So you might be able to develop an actual profile that can reflect health risk over time in aging. You see,
let me give
start
you an
when they're young,
example.
and then just profile them all the way until they're old.
Kind
That
of
was
hear
the
you,
thinking.
but
So
it
mitochondria-
seems to me that just getting to the point where you can interrogate an individual mitochondria
It's not a small problem.
is huge in and of itself.
That's why it's a 20-year goal and
Yeah.
a $500 million investment.
Yeah.
Yeah. But the idea of being able to assess mitochondrial function from the point of view of something that's useful to humans, we know that humans are exposed to heavy metals, for example, and endotoxins and things like that. So what we could do in animal studies is take a female animal, expose them to lead or mercury or both, have them gestate a litter of animals that are now exposed to second generation effects or do a third generation effect, and then chelate it and look what happens to their mitochondrial function. Can we reverse it to the full health of an animal that's never been exposed to those toxins at all? And we can assess that at the level of individual mitochondria and the process that's involved in that deep level of biology.
So you're aware that mitochondria move and merge and reform and are destroyed, right?
Yes.
You have your little probe that goes into a mitochondria. Well, at a later point, it will not be there.
If it's embedded in the membrane, it should stay there. I mean, it's possible that a microtubule or a fiber would potentially scrape it off if something sticks out. But if it's a nanoparticle with a proton permeable membrane with indicators inside, and we're probing it with photosignals, it should move with the mitochondria.
And the mitochondria gets broken down, destroyed.
And those probes would be let loose, yes. Or migrate to another
So the
mitochondria.
tube obviously has to be flexible. I think I saw a thing about targeting. I mean, do you have an idea of how you would actually get it to into a mitochondria?
No, not a clue. But the tubes are,
How to find the mitochondria.
Yep.
Right.
To penetrate.
yeah, nanoparticles, the technology for immersing nanoparticles selectively in membranes exists. But the building of a 2 nanometer needle with, I mean, a femtometer channel down the center. That's never been
You
done.
want to be specific for the mitochondria as opposed to other organelles or the cell membrane or so on.
Well, we don't mind actually sampling other organelles too.
Like to know what you're looking at?
Oh, yes, absolutely.
So do you think it would be useful to simply sample from the intercellular fluid? You know, just try to do single cell rather than go within the organelle first?
We would do that, I'm sure, because we want to have a comparison basis when we're looking at the internal environment in a mitochondria. The cytoplasm is the reference, the comparison.
We are out of time,
Okay.
but this has been great. Thank you so much.